look at this here. Let's say that I just want to do something similar to our existing particle system, because we already look at this here. All right, so let's take a look at this here. Let's say that I just want to do something similar to our existing particle system, because we already wrote some code, right, that was for an existing particle system. And that particle system, that's not what I wanted, was just a thing that like spewed little hero heads kind of out of a known location, right? So I believe this was the code that we used for our particle system right here. So what I want to do is I want to kind of just grab this particle system and say, well, let's go ahead and just get this particle system working as an example inside our particle system here. And maybe that'll give us some insight into what we would want to do. So I don't really know what we would call this, but it doesn't really matter. Like I said, I'm just going to start working with it a little bit and just kind of get it to the point where it's something that we could run, and we won't really think too hard about anything else. So I guess we don't need that either. Oops. So here's kind of the outlines of what we did back in those days. If you don't remember this, now would be a good time to go catch up on those old episodes about the particle system. Like, there were only 2 of them. It shouldn't take very long. So the particle spawn index is just a thing that's saying, hey, let's create some new particles here. And you can see what we had for particles. And maybe this is a good guide for what we should be storing. We had a position for each particle, we had a velocity for each particle, an acceleration for each particle, and then we had a color and essentially a delta on that color, right? And one of the things that we were doing was we were spraying nothings, I think, in honor of Sean Barrett and his libraries at some point. This obviously is not none of this is relevant to this stuff, but we need at least that part. So there's a bitmap ID. It was using the head bitmap ID, and each particle, I guess, had its own bitmap ID. I don't think we will probably want to do it that way in terms of using bitmap IDs like that, because just there's some kind of complexity there. I'll just quickly give you a little bit of a sketch of why we probably don't really want to do that. And we want to do things slightly differently. So let's say that we want these to be rather efficient. So what generally happens is that we want to render all of our particles, when we're talking about having a large number of things. So for example, we use the number 4096 kind of arbitrarily, but if you think about how many that is, right now a single particle system, if it actually had 4096 particles, would have more actual sprites in it than anything else in the game combined, right? So like on the screen right now, there aren't even 4096 things. And what that means is that when we go to render these are going to be the most expensive things to render in terms of getting raw data throughput to the card for like positions and stuff like this, position and color and whatnot. So if you take a look at what this means, this 4096 number means that we don't want to be doing anything per particle, right? We don't want to call the graphics card one time to do something for each of these, right? Because if we have a fair number of particle systems on the screen and each one of them has 4096 particles or something like that, it's quickly going to add up to way too many interactions with the graphics driver and way too much overhead. So one of the things that can create that overhead, depending on the circumstance, and there are cases with bindless graphics APIs and stuff like this, where there are cards that don't have these limitations, or drivers that don't have these limitations. But in a lot of cases, especially on older hardware or on hardware that might not be quite so gaming dedicated, like maybe mobile graphics, who knows? Typically changing the texture is bad. So a lot of times you don't want to have to change what that, remember we kind of, like with OpenGL, we would say like GL, we'd have like this text image 2D, and we would say like GL bind texture, right? And we would say, here's the texture that we're going to be using for drawing. Well, doing that bind, it costs. That is a cost. And so having to do that manual binding is not really acceptable because it creates way too much driver interaction and potentially way too much card action as well, depending on the card. And so what we would rather do is have a way of having all 4096 of our particles just all in a nice big buffer, right? Where we can just point the graphics card at it and say, hey, we're just going to set up your state once, and then I want you to process all of these particles, right? So what that means is that we don't want to have to change particles for each, change textures for each particle, because if we did that, we would have to talk to the driver again, and again, create more and more bus traffic, possibly more card operations and so on. So, best case scenario for us, if we did want to change textures, like actually change textures per particle, well, what we would do is say, like, okay, so there's the position, you know, of the texture, of the particle for each particle. There's like a position, a color, position, color, and so on. And then we'd put a texture pointer here, right? An actual card texture pointer here. And that actually is possible on some higher end cards, right? So it is actually possible to include what texture you're using as part of a buffer that you hand to the graphics card and say, hey, here's the position and the color and the texture pointer of each particle as you render, and have that all be done in one big batch. That is possible, but it is not very widely supported, at least, you know, not if you're talking about, you know, hardware from 2-4 years ago, whatever, or even some hardware from today that's not, you know, high-end or whatever. So instead, what there are other techniques that kind of approximate this. So if you do, like, you know, one solution to this that's very simple, right, is just say, well, you only get one texture per particle system. So, you know, if this particle system, all the things have to be little spheres, or all the things have to be little stars, or whatever, right? So that's one solution we certainly could go with, is saying, well, okay, we just pick one texture and we stay with that texture, right? But there are actually other alternatives that are sort of similar to this that we could use that don't involve that kind of a limitation. So we could have different particles in the same particle system using different textures, which I'm not even saying we need that, but I'm just pointing out that it can be done. And the way that we do that is, instead of trying to switch the actual texture that we're using, what we typically do is find a way to pack more images into the same texture. So for example, one thing you might do is say, well, okay, if this was my texture, maybe I divide it up into 4 pieces, and I put one particle here, I put another particle here, you know, I put another particle here, and I put another particle here. So here's my 4 particle, you know, bitmaps. And then what I could do is just in here pass sort of something that tells the graphics card what the UV coordinates for the particle should be, and then I just pick one of them by picking the region of the texture that I want, right? And this is similar to like the texture atlas technique, right, for example, that you might see talked about, where you're basically just packing sprites into a single texture so that you don't have to tell the card to change textures every time you want to pick a different image out of it. Okay. Similarly, another thing you can do is, a lot of graphics cards now support the concept of texture arrays. And what a texture array is it's a single texture handle that you set up. So when you do a texture handle, it's a single one you set up. But then you can actually pass an index here, right, effectively, which says which sheet of like a stack at that address, right, you want. And so you pack these guys in there, right? The square goes in the back, the triangle, right? And so then if I pass index 0, I'm going to get this one. If I pass index 1, I'll get this one. Index 2, I get that one. And that has some additional advantages over the Atlas technique, assuming that everything is going to be the same size like that, because obviously these things have to all be the same size. They're all like, you know, one texture that's kind of has different slices to it. It's like a 3D texture almost, right? And there's some benefits to that, and the benefits are that you can have better control about what happens at the edges and during MIP mapping and things like this. Similarly, another thing you can do is this. Similarly, another thing you can do is, a lot of graphics cards now support the concept of texture arrays. And what this, because if you think about what happens here, as this texture gets downsampled, if you were to do, say, MIP mapping, or if you look at what happens when I cross over the boundary here, well, if I wanted to, like, make a repeating pattern or something like this, I couldn't really do it here, because as I cross over this texture boundary, I'm going to see the star, right? But in this case, I don't have anything on the other side of the texture map, so I'm free to use the sort of wrapping and clamping texture modes that I would normally use. And so sometimes that, and plus the bitmapping not filtering them down together, those things can have, reasons why they might be important. I don't think they will have any relevance on Handmade Hero for the most part. But for certain higher end applications that you might be considering, these things have, potential bonuses. There's a difference between them. And of course, the Atlas can do something that this can't do, which is to make each of these be different sizes, right? I could choose to partition my thing quite a bit differently and pack the rectangle down in a small one and, the circle over here and whatever. So you kind of also have this notion that a texture atlas is a lot more flexible for packing the things in, but one of these texture arrays is much more flexible for actually using the textures at the end of the day, because they can still take advantage of proper bitmapping that doesn't degrade as you get lower, and then also border modes, which you wouldn't have available in the other one. Which is, even that's not entirely true. Texture atlases, if you are implementing your own texel fetching in like a shader, for example, you can overcome some of these limitations, or sometimes all of them, depending on how expensive you're willing to make that texture sampling be. But point being, this one is basically free. Like the card will just do this right. So, it's a way to get all of those modes back pretty much for free without having to do any kinds of additional math in the shader to fix up texture coordinates and pick things differently. Okay. So as far as particle efficiency is concerned, that's just something we want to be aware of. Changing the means do is find a way to pack more images. Actually, just pointing out that it can be done, and the way that we do that is, instead of trying to switch the actual texture that we're using, what we typically do is find a way to pack more images into the same texture that we're using, and the way that textures, which particles in the same, that kind of a limitation. So we could have different particles in the same particle system using different textures, which I'm not even saying we need that, but I'm just pointing out that it can be done. And the way that we do that is, instead of trying to switch the actual kind or that texture solution, we certain things have to be little spheres, and the way that we do that is instead of trying to switch the actual texture that we're using, what we typically do is find a way to pack more images into the same texture. So for example, one thing you might do is say, well, okay, if this was my texture, maybe I divide it up into 4 pieces and I put one particle here. So as far as particle efficiency is concerned, that's just something we want to be aware of. And probably what I would say on Handmade Hero makes the most sense is to just do something kind of like the Atlas, where we just, oh, excuse me, I'm very yawning in here, where we just want to take a single texture and put, the 4 bitmaps or whatever, or 10 bitmaps, 16 bitmaps, whatever we want to do for our particle systems, just pack them into one texture. I don't think we're going to have too many of them. And then just use that one texture by selecting out of it using some UV coordinates. And in the simple case, what we'll do is we'll just actually pass full UV coordinates for the particles, full rectangles, and UV coordinates. But if we ever get around to playing with shaders and want to kind of explore that a little further, there's other things we can do there where we just pass down something much more simplified, like the center of the particle and its size, and maybe a representative's orientation, and then just an index for which one of these we want. And then we would have one of our front-end shaders in like the geometry shader side of things. We would then have that do sort of this amplification of that minimal description of the text of the particle into the actual UV coordinates, take that index and build on the actual UV coordinates and so on and so on to feed the later stages of the graphics pipeline. So right now we'll just build it explicitly on the CPU, but you can do more compressed representations of particles, and should if you're going the shader route, because if you know your target hardware always has stuff like geometry shaders on it, because not all of them do. All right. So coming back, I think we do want to sort of leave this as an open issue at the moment and say we'll deal with that a little bit later, because that's really more on the rendering side of things. So for now, what we'll say is, the bitmap ID is not something that's going to be per particle, so we really want these other things per particle, and we don't really want to deal with the other stuff just yet. If those are the things that are going to be per particle, and we do want to make them be sort of lined up this way, then I think what we want to do for the particle system is again, kind of think of this a little bit SIMD-wise. So to me, I kind of feel like I would probably want to do this as SIMD things, where we kind of have something like this, where we kind of say, like, okay, however many particles we want in our systems, we'll divide them by 4, and so that we can kind of keep our particles in a nice SIMD fashion, right? Something like this. Because I do want to be able to process these things relatively quickly, and we should process them 4 at a time. And we can always know that we've got 4 of them at a time, because again, particle systems, the count is very flexible. No one's going to care if we have exactly 63 particles in a particle system. We could always make it 64 and be fine, right? So I'm going to go ahead and actually delete these, because I want to kind of make them a little more explicit. So if I was to do that, you could see me making essentially the variables that we had in our existing particle system pretty trivially. I don't know that we actually need them all, but let's say that we did. We would have a particle system that kind of looks like this. So we've got our color. Oops. And I guess I don't really know. So I guess what we were doing before is we just wipe the color out when we just will respawn a particle. Oh, we just respawn the particles in a front. So that seems fine too. Never mind. All right. So yeah, this is what we had before. And it'd be pretty easy for us to implement things this way using sort of, again, the SIMD instructions. And all I'm doing here is just saying, okay, so let's suppose we've got those things. I'm just going to do sort of the SIMD version of those so that all of the operations that we do will operate on 4 particles at a time. Now, it's kind of annoying. You can see why you probably would want auto-vectorization for these sorts of things, because you can kind of see that what we're going to have to do here is just a lot of unnecessary busy work when we're actually sort of trying to work with these things, because in order to deal with things in the sort of M128 sense, we forego a lot of things that would be nicer, such as the nice math notation that we had for the rest of our sort of math ops. And that's purely just because, these languages weren't designed very well to handle vectorized ops like this. So sometimes you can get away with just not doing it, writing it in scalar. And when you do write it in scalar, then you get kind of this thing of, well, maybe the compiler will vectorize it for me. There's actually ways in LLVM, for example, and Visual Studio to sort of say, hey, would you try to take this code that was not 4 wide and make it 4 wide as best you can, stuff like that. It never really can do probably as good as you could do by hand, but sometimes it's surprisingly good. And I believe the Intel one, the Intel auto-parallelizing one, was supposed to be pretty good. You could mark up your code to kind of give it hints about how you should do stuff. And once you did that, it was pretty good at generating what you would want to generate. So, over time, hopefully these sorts of things will become easier and you won't have to do them so much by hand. Anyway, so if that was a particle system, what is this saying? Max particle count average. Oh, yes. Sorry. All right. So what I want to do here is I want to just start to get this stuff into shape where, I'm going to literally try to just implement exactly the same particle system that we had in the first place, and I'll try to get that running. So this is just going to be like a play around. We don't really know what it's going to do, but we do know that it's going to be operating on one of these particle systems, so we're pretty sure it's going to be doing something like this, right? So we need to do some spawning. Obviously, the spawning will make will be exactly what you'd expect. We need something in our particle system here. I guess I don't know exactly how we want to do this, but we would want to have something where we keep track of this next particle thing, because that is something we want to do. And presumably we want to spawn, I guess we would want to spawn 4 particles at a time. Since we already had this spawning 3 particles at a time, it seems like spawning 4 particles at a time would not be particularly problematic, right? But, you know, I don't know. That may be something that for certain things is not tenable, because you may not want 4 particles spawned every frame. You know, that might just not make very much sense. So we may have to make the spawning of particles be something that operates individually and doesn't actually use the SIMD part as much, but I don't know. For now, we'll just keep it spawning in clumps of 4, because that will be the most efficient, and we'll just see where we get. So I'm going to say this is like next particle 4, because it's actually referencing into here. You know, it's referencing into clumps of 4, as opposed to actually talking about an absolute particle index. So I'm just kind of sticking a little. It's not a very good convention, not a very rigorous convention, but it's just something to kind of make me look at it twice and just go, oh right, that's a thing. That's not directly talking about a particle index in an absolute sense. So if we do this and say, all right, let's assume that we can grab a particle out this way. We have our index here. And maybe I'll just call that PI for short. Or particle index, let's call it array index. So in here, we're going to grab out one of these particle indices, and I'm going to do that by saying that it's whatever the next particle 4 was. I then need to check for wrapping on this one. So if it's greater than max particle count 4, then we're going to reset it. And in here, when we look at this, we don't need the for I loop anymore, potentially, at least not at the moment. So I'm going to get rid of it because we're spawning 4 at a time, and that's fine. So in here, we'll just say, all right, once we do know which one we've got, we now have the ability to sort of reference this slice here. And, excuse me, we just need to set all these guys up, right? So I'm not sure if there's a smarter way to really structure this. I'd have to think about that in a way that makes it easier for us to talk about one of these guys directly. You know, you can kind of imagine we sort of want to talk about the PX, PY, PZ, and all that sort of stuff. We don't want to have to keep doing lots of different sub-addressing. So it's a little bit janky, again, so I apologize. I'll have to think through whether there's a convention that I would like to use that'd be better here. But, you know, essentially this is what we're doing. So, you know, before we were doing this sort of thing. And so I'm just going to do that thing again, exactly what we were doing there. And the particle system entropy, I feel like could be also stored with the particle. I don't feel like we need to have any kind of anything special going on there. So we could have a random series here, which is just the entropy for this particle system. And we could coalesce that. In fact, you know what I guess we could do is just say, hey, why don't we just pass that in? So there's a random series that we get that's the entropy for this guy, and that's all good. In fact, I could actually just do it this way. And then well, that kind of won't advance, so we'll do that. And then I just need to do the rest of these guys exactly the same way. Nothing going on here particularly interesting. I'm literally just sort of translating this into something that's a little bit more SIMD-ish. And I'm keeping all of the same values we had before, because why not? Wait a minute. He says, so this random between was actually 7 times. Okay, that was almost a copy pasta there. I was like, wait a minute, what did I do? There we go. That's the actual one. So there's the random between, and no z. All right, so that's what we're doing with that. And so now we kind of have this this sort of additional nastiness, I guess, is that each of these is trying to do 4 particles at a time, and this is only generating 1 piece of entropy. So we actually need to call this 4 times, 1 for each particle piece, right? So these are actually like, you know, set ps, not set1. There we go. These are actually sort of ones where we have to do this, right? Again, not particularly pretty. We would rather have a way of writing this a little cleaner. So, you know, I think what I would probably do at this point is say, you know, so, I think, I think what I would probably do at this point is say, you know, maybe like set to expression or something like this, and have a way of passing that expression in there, and then just replicating the actual expression. Because that seems a little bit easier than trying to keep copying these. So that way I can say like you know, maybe I'll make it even shorter. So there, you know, I'm going to say, okay, here's an expression. Instead of having to replicate that 4 times, I'll just say, you know, do that 4 times for me, right? And the same would be true for all of these. Should probably indicate at least that it's a set. And that seems a little bit better, because then I can just sort of wrap these, and that we're already kind of verbose here, and so this way that keeps down that sort of unnecessary duplication, which would just be a pain in the butt to maintain, because, you know, I'm going to come back through here and decide to make changes, and I'd have to make it 4 times, and that's just annoying, right? So yeah. So finally, we want to set that acceleration as well. And again, this is pretty straightforward. Not a lot going on here. So those are the accelerations, and now we just have the colors. What did I do this? Those are CR, oops, GBA, and the CRGBA here is just, again, another randomization. Yeah, these also get wrapped, and they should work. I hope. He says confidently, unaware of what was about to befall him. And last but not least, we've got that delta color, which looks like the simplest of them all. Which is basically all set to 0 except for the alpha value, which decrements. So in theory, I think that should do it. Obviously, we got to replace these effects entropies here with regular entropies. And that's about it. So, yeah, now we've got sort of our Lagrangian and Eulerian situations here, and for these, you know, again, we can still have these if we want them, because since each particle system is sort of a self-contained thing, we can definitely do sort of the particle to grid situation. The problem is, it will definitely be a bit of a downshift for us, because in order to do that kind of thing, we are forced to downshift every time on each batch of particles because there wouldn't really be any way for us to have the particles right into a grid without picking out individual pieces, because their location in the grid will depend on their XY coordinates, and of course their XY coordinates are all going to be different in each batch. So, for example, this stuff right here, where we pull out the XY and we put it in the grid like so, that's really not going to cut it. There's no way to do that for wide in SSE2, right? You just can't do it. I wish you could, but you can't. Later on, this is why AVX 512, if I remember correctly, was such a big deal, and I was hoping we would get it in desktop chips, and we will, it's just taken a really long time to actually get any kind of installed base on that because it was only in Xeons and blah blah blah. But the AVX 512s were really nice because that instruction set for the first time, I believe, had the parallel gather. So you could basically say, like, okay, do this memory fetch. Like, you could go get particle cells or whatever. And that's about it. So, yeah, now we've got sort of our Lagrangian and Eulerian situations here. And for these, again, we can still have these if we want them. Because since each particle system is sort of a self-contained thing, we can definitely do sort of the particle to grid situation. The problem is it will definitely be a bit of a downshift for us because in order to do that kind of thing, we are forced to downshift every time on each batch of particles because there wouldn't really be any way for us to have the particles right into a grid without picking out individual pieces, because their location in the grid will depend on their XY coordinates, and of course their XY coordinates are all going to be different in each batch. So, for example, this stuff right here, where we pull out the XY and we put it in the grid like so, that's really not going to cut it. There's no way to do that for wide in SSE2, right? You just can't each batch. So, for example, this stuff right here, where we pull out the XY and we put it in the grid like so, that's really not going to cut it. There's no way to do that for wide in SSE2, right? You just can't do it. I wish you could, but you can't. Later on, this is why AVX 512, if I remember correctly, was such a big deal, and I was hoping we would get it in desktop chips, and we will, it's just taken a really long time to actually get any kind of installed base on that because it was only in Xeons and blah blah blah. But the AVX 512s were really nice because that instruction set for the first time, I believe, had the parallel gather. So you could basically say, like, okay, do this memory fetch. Like, you could go get particle cells or whatever for things for wide, right? So that way you didn't constantly have this thing where you had to like downshift every time you were going to work on something that happened to sort of look up into a texture or a grid or whatever, and where each lane was going to want a different location. There's no real reason why that has to downshift, right? Because you can always do your memory ops for wide. It's just the Intel instruction set didn't have for wide memory ops or anything like that, for wide fetch. So there you go. Anyway, yeah, so I think I will forego the grid for now, and we may want to support that, but rather than put the grid in at this point, I don't know that I really want to do that, because I think we want to probably be SIMD particles. Maybe I'm making a huge mistake. Maybe we just shouldn't SIMD the particles, because the number of particles we'll have won't be enough to make that be important. So, maybe that's just dumb. I don't know. But anyway, I'm going to go through here and just say, all right, so then let's do the particle, the actual particle count. And let's go through each of the individual particles. And then in here, we should be able to just nuke the part that has to do with the grid, right? Which was that. And I'm pretty sure that the cells did not, it was just the dispersion. That was all we were using. So in theory, we should be able to do everything else that we wanted to do, and we shouldn't have to worry about, the fact that we nuked the grid, because the only thing the grid was doing was keeping particles from clumping together. So we should still see a viable particle system with the grid turned off. All right, so simulating the particle, again, this is pretty much just all we really need to do. Now, if we want to, we could implement some of these operations on MM128s if we want to. I'm not sure to what extent that would work okay. I think they actually might already exist in some of the Intel includes, but I think we would be able to do something like, think we would be able to do something like, You know what I'm saying? I think we would be able to say, like, let's overload an operator that will operate on M128. So if we want to, we don't really have to micromanage it quite so much. Maybe we can just sort of leave the equations roughly the way that they are for the most part, and then not have to worry about it so much. And so if we did something like that, you can imagine like the particle situation here. I don't know if we can do plus equals without it being a member function of the M128, but like these other ones we can. So for example, scalar times, if we do like a scalar times, it should be pretty easy to make that work, right? So we should be able to do that. Now, unfortunately, we can't do the vector version of it, so it's still going to look kind of like this, right? Which is not great. Like, it sucks to have to blow that out in that way. But I'm not sure what the easier way to do that would be, notationally speaking. One thing we could do, again, is try to make some kind of a macro that helps us with that expansion. We could also do something that did slicing of these things, and I don't realistically know that that would compile okay. But we could try. Like, we could try to make like a little utility that just does like pointers and then rely on the compiler's optimizer to sort of figure out what we were doing there and not, do a bunch of indirection. It's certainly plausible that that could work. And if we wanted to do that, it would be more like, get a pointer to the px, py, pz, and then have a vector type that just operated on pointers to things, and then hopefully it would be smart enough to know that they were not aliasing. But would it really know that they weren't aliasing? I don't know, et cetera, et cetera. So it's a little tough to say. I'm not sure how well it would do. This is again why you kind of want these things to be more first-class citizens of the language, so you don't have to try and think through like how am I going to kind of convince it to sort of deal with these things that really it should have just kind of naturally known how to deal with if in a better situation. So similarly, we can create one of these for the multiply operator where there's a scalar on one side. So if we have like something like this, where there's a scalar multiply operator, create one of these for the similarly, we can. So similarly, better situation. So similarly, we can create one of these for the multiply operator where there's a scalar on one side. So if we have like something like this, then I can say like, oh, okay, set 1 PS for that A, and then, multiply it by B, and that's the result, stuff like that. So we can still use a certain degree of math, even if we don't try to do anything fancy. We can still at least do some of that there. And the same would be true, again, for the color. Like so. And the only thing, like I said, that I'm not sure about is if there would be any way for us to really do like the plus equals and so on. Now, obviously there is one way we could do it, which is to wrap the M128 in our own struct and then put the plus equals on that, which maybe we should do. I don't know. But I don't know that I can do a plus equals externally, right? I'm pretty sure that if I tried to, I would end up in a situation, I should probably finish this one as well before I start trying to compile. I'm pretty sure that I would end up in a situation where that would not work. But that's okay, maybe we should wrap it, and that's fine too. Anyway, so if I go through here and say, here's my equation. Then when I've got, okay, so all of these things, these are all scalars that are all happening here. And then finally I get to sort of my DDP, which needs to be expanded out. And now that I think about it, I could probably at least save that expansion by just making that a local pointer, which I probably should do. But anyway, you can see like these are all just scalars anyway, so that's all fine. We just need that DT. So there's the DT. I don't know why we do a square. Is it a little bit odd? This equation doesn't look quite right to me. Why is it look like that? It's doing a cubed addition of the. This looks like it's doing a cube. But why is it doing a cube? There's no real reason why it would do a cube here. I think that's a bug. I feel like this should just be this. Right? That seems like a bug. Why is it multiplying? Because 1/2 AT squared, when we went, you remember we went over the equations of motion. 1/2 AT squared is the equation we're looking for here. And for some reason that was 1/2 AT cubed, which doesn't really make a lot of sense if we're honest about it, right? Doesn't make a lot of sense. So anyway, not sure what was going on there. But in here we can take a look and say, okay, so now we've got the system DP. And in here we could say like, okay, the system DP X, Y, Z, AI, right? And so we need to pass that DT. We never really did pass a DT here. And if this is an update, it's going to want one of these. And so that's all fine. But like I said, these plus equals would be a problem for us. So I'm not sure what to really do about that. Now here's an interesting thing. Here's a interesting thing. Here's a thought. Here's a thought. What to really do about that. Now here's an interesting thing. About that. Now here's an interesting thing. Here's a thought. And this is kind of ridiculous, but I'm going to say it anyway. Because why not? So here's a thought for you. If you take a look at what this thing looks like, right? The px, py, pz for an individual one of these particles is separated by some number of intervening values, but they all happen to be like the same. They're homogeneous, right? They're all max particle count 4. So if you think about it, if we were to take one of these things and say, well, we've got a particle system and we've got this individual thing, maybe called a particle v2, v3, or v something, right? So we have something called like a particle v3. You could imagine us saying, well, okay, what if there was an x for it, and then like an ignored, something like this, and then a y for it, and an ignored, and then a z for it, and an ignored. Right? Like, just hypothetically speaking, what would it look like if we told the compiler that we were pointing at one of these particles, and we actually gave it a pointer to somewhere inside this px array, right? Well, in theory, the x, the y, and the z at that point would be pointing into the right areas in their respective arrays, right? Because they're just this far apart. There's that many interceding values to get to the y, right? Because like if you started on the 0th px, you know there's max particle count 4 mm128s before I get to the 0th y. And if I was at the first x, I would know there was still max particle count 4 mm128s in between me and the first y. So like 2, 3, 4, 5, they're always separated by that stride. So one way potentially, right, of simplifying this down to something that would be easier to work with potentially would be to say, well, okay, really I could get out the particle here. I could say that I have a particle v3 that's pointing to the p, and we just tell the compiler that we have one of those, and that we're pointing at, you know, the px of the system, you know, whichever index into the particle system's arrays that we have, that's the one we're pointing at, but instead of treating it as just a single px value, treat it as this sliced particle thing. And then, in theory, we could write the operators on that thing, right? That's just something we could operate on directly. So we could do something there. We said, like, okay, there's our particle. And so then we could say, well, star p equals, you know, well, now I think about it, that part won't get any easier. You can at least do that, right? It's a little weird, right? It's a little weird, but, you know, that's certainly cleaner to read, right? So, you know, that, to me, seems like probably a win in terms of constructing this code, right? And we still have a bunch of funny business to do here, I guess. In some sense, because if we want to have operators on these guys, then we would need to pull each one out. But, you know, not that big of a deal. Right? So it seems like that would work. I don't think I've ever done this particular ridiculousness before. But, you know, I mean, I don't see an obvious reason why you couldn't do it this way. And since the stream is kind of winding down here, you know, we can at least, in terms of time, we could at least test this out and see how it goes. But like I said, it seems like something that would work. And of course I would have to make a version of these that was actually 4 wide for the colors, which I can do in a second. All right, so something like this. And so I don't know, will that work? Let's find out. If I also make a 4 wide one of this, well, it's really no no different. This, well, it's really, if I also make a 4 wide one of this, well, it's really no different. It's exactly the same thing. So it's just RGB, right? Okay, so there we go. Clean that up. And so in theory, I think that would work. I don't really know. But I don't see any reason why it would confuse the compiler too much. And then down for these things here, in theory, we could make operators on these. And so in theory, we could do something like, compiler too much. And then down for these things here, in theory, we could make operators on these. And so in theory, we could do something like, this guy plus equals some way in which these guys get upconverted, which I think isn't difficult, probably. I'm guessing. Yeah, because at the end of the day, once we have one of these, it's pretty easy to also read out of one in a way that collapses it, right? So I could also say, equivalently, right? If those are, if I'm operating on one of these, don't carry the particle v3 through. Instead, you will want to use something like a v3 to carry the data. So for example, let's do this one more time. I'm gonna maybe, how do I want to do this here? So yeah, I could do it this way. Let's say I just did struct. So yeah, I could do it this way. Let's say I just did struct particle, and in here I just had these guys. Right? And so what I could do is say, okay, there's a way of just getting a particle. By just passing whichever particle system it is that you were talking about, and then the index that you wanted. And then it would just do exactly this operation, but return one of these. Right? So, result.p, dp, ddp, c, dc. And what I might do in this case is, rather than do it that way, I might actually have you pass in the particle to fill out, just so our debug mode doesn't suffer too much speed hit, because, in optimization mode it would clean that out nicely, but in debug mode it's not going to do something particularly smart there. So I just, since this is a loop that'll get run a lot in debug mode, I don't want it to be too unwieldy. So yeah, so I could say particle, I don't know, I'm just going to call it A because I have no real reason to call it anything in particular. System AI A. So now it's just, and there we go. I think this is not anything we want to preserve. So I'm going to go ahead and move those guys down here and nuke them temporarily, probably permanently eventually. Okay. And that is not supposed to be an ampersand. So let's take a look at that and see how we feel about that. I don't know, it's a little wonky, but let's just take a look. So now we can do the same thing down here, and I'm going to go a little over time because I started pretty late, so I'm going to go for a few more minutes. So I'm kind of enjoying this weird exploration here. I'm going to do the same thing down here to get the particle out, and then I'm just going to say, like, okay, so we've got these things, right? And I want to do, like, math ops on them. So I want to do a single operation and update this particular particle. And I want to do that using its DDP and stuff like this. So I want to say, you know, I want to say a.ddp here, and I want to say a.dp here. And I want that to just magically work, right? So I want to have that happen. I believe these are technically should look like that. So yeah, it's not great because I still have to dereference it because it is a pointer, I believe. Yeah, it is a pointer. So, you know, I would have preferred that somehow it not be a pointer, but I don't know that there's really any way to do that and still be able to write back to them. I suppose we could try making it a reference, but that would be kind of hard to do the construction on. We'll think about that. But for the moment, we'll just leave it like this. And then, you know, like I said, this would all presumably get simplified down into something that looked a lot more like the original. So it would be something more like this. Right? Yeah, so I don't know that I want to do this guy yet because ifs will require some special handling in the SIMD, so we'll leave that out for now. And we don't want to deal with the rendering yet, but otherwise, most of this stuff is okay. You know what? Like this is just one thing here. So this is, again, star A dot C plus equals dt times particle dc, right? And similarly down here, this seems pretty straightforward as well. This is just clamping the color, but I don't know why we don't just clamp the color. I'm not sure why it, I guess because we want to be able to set the color to something other than, so the output color gets clamped. So I guess that's just part of the rendering, so that's something that we don't, I guess, have to worry about just yet either. Okay. So now, if you take a look at what we're doing here, right? We've kind of got the stuff working that we want to work, but we've got some operator overloads that we need to figure out how to do. Because now we've got sort of these particle v3s here multiplying by scalars, and then they're getting added to this and blah, 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 right? But that's okay because we can write those things pretty easily. If we take a look at what we've got here, if we want to do one of those particle updates, right? If we wanted to say, okay, let's make a plus equals operator for our particle v3, right? We could pretty trivially do one where we just said, okay, let's say it takes a v3 in. Well, all we need to do to make it take in our v3, well, I guess we need to be more specific, we need a sliced v3, right? So we just need, you know, a v3 that's 4 wide, right? We just need something that's this. I don't know, something like that, right? Where we've got a 4 wide one of these. Well, if we had a 4 wide one of these that came in, we could then say, okay, well, then that's pretty easy. The x is just plus equaled, the y is plus equaled, and the z is plus equaled, right? We'd just be adding the pieces of these guys that we know we already have. right? So hopefully you can kind of see where I'm going with this now. So when we have this particle v3, we can, if we want to, just do this operator on it. And when we try to do a plus equals operation on it, we will actually get exactly the operation that we want. Right? We'll just get the piece of this. So the question is just, well, all right, how do we then get, and these, by the way, are, I guess, not super relevant. So I just said we can't add those, so this is what I actually meant to type. Right? So in this case, I'm just saying like, all right, let's do it and pretend we have a thing that comes in here that's got the values we want to add. We'll add them. So then all we have to do is write the opposite style of conversion, right? When we see a scalar times one of our particle v3s, well, we don't want to propagate. This is a giant thing. It's like, you know, it's a massive object. We don't want that whole structure to be copied around, but we don't have to, right? What we can do instead is just say, well, all right, if you were to see one of these guys where you wanted to multiply a scalar by one of these particle v3s, it just generates just the part that it wanted to, just the part that we actually cared about, right? So we could generate a result here, and that result would just be the x, y, and z of the scalar multiplication with the parts of the giant slice that we actually care about. So we're kind of slicing off just the x, y, and z at this point and leaving everything else. Right? So now we can see how this expression will start to take shape. How do we make this thing work? Well, okay, expression will start to see how this... So now we can see how this expression will start to take shape. How do we make this thing work? Well, okay, it's going to try to take one of these guys, which is a particle v3, right? It's going to try to multiply it by a scalar. So when it does that, it will evoke this operator. Let's put it in line in front of. That operator will take and slice away just the x, y, and z that we actually wanted, and then return that as a v3 for x. That will then get multiplied by a scalar again, right? So that means we're going to need one of these. It's actually the exact same code. Right? And then it will try to add that to essentially an exact same kind of the other side there, right? So we know that this side will generate the exact same thing. So then we just need a operator plus for these guys, and we're done. Right? So now I think, what is this missing type specifier? Oh, sorry. This will just return one of these guys. That's the typical ridiculousness in C++. No operator found for what? Oh yes, this is an PS. Keep forgetting we don't have any overloaded operators for the M128s, so anytime we're actually doing them, we have to use the SSE intrinsics for it. Not a problem. Oops. Okay. And since this is a scalar, I really just need to blow this guy out, so we just need one of these. Like so. All right, same thing here. Just need to write this in SIMD friendly way, which looks like this. Same thing, blow out the scalar, and then we want to do the mul ps. Oops. And really, we can write this in a better way, which we could do tomorrow. We could write this in a slightly better way, which is to just make these guys first loft up particle B, just make a thing that translates a particle B into a V34X, and then we just use that, right? So that's a much easier thing than writing that every time. So now you can see these two guys compile just fine. And now we just need the 4-wide version of the same thing, right? And then we're good to go for the colors. So I'll do that tomorrow. Don't want to run too much out of time there. But that's it. All right, so I'll go to Q&A for just a little tiny little bit. In case anyone has any Q colons for me. Martin says on MSVC it is possible to create a non-member inline operator plus equals for MM128. It is done in the same way as you did for the other types, but for GCC Clang you cannot do plus equals for MM128 because they already have it. Well, you know, that's not bad, right? Because we could if 0. We could use if 0. Not sure why I made it a member. That's a good question. I think I was just thinking I had to for some reason. I use these features of C++ fairly rarely now, so I don't remember a lot of the minutia. I don't really remember a lot of times like what they pass. Does it pass a reference, for example? Yeah. So I assume that is roughly, roughly what they would want. Yeah. Soy sauce the kid. Instead of doing the particle v3 struct, could you accomplish the same thing with macros and some pointer math?